Okay. So where did we leave off? So let's review a little bit, because last time we went a little fast. So we were trying to prove the Paley-Weiner theorem. So this is f is an entire function and grows at worst exponentially. And I need to know that f has moderate decay. F restricted to the real line has moderate decay. That I need to know, because without that assumption, how do I even define the Fourier transform? So f is entire, grows at worst exponentially. Doesn't decay, grows. It grows exponentially at infinity, but at worst exponentially, not e to the z squared or something. Then the Fourier transform has support inside minus m, right? And the converse is easy. So it's an if and only if. If the Fourier transform has compact support, then you invert the Fourier transform, and it's easy to show it grows at worst exponentially with that exponent m and is an entire function. That part's easy. The hard part is, how do you force a function to be zero, Fourier transform to be zero, right? Okay, and just a reminder of the proof. So we did this in 3 stages. Stage 1 was to assume more about the function, assume that f of x plus iy in absolute value is bounded by a constant e to the 2 pi, not z, but y. That we want y growth and moderate decay in x for all x. If that's true for all x, for all y, this is for all x and y, that we have this. If this is true, then there's no problem reversing orders when you put in the there's no problem pulling contours, right? We pulled contours, then we pulled contours, so we got a bound for f hat of xi. If, let's say, xi is bigger than m, then we pulled contours up or down. Maybe it was down. We got exponential decay as soon as y was bigger than m, but we can pull y all the way down, and and we can pull contours so these end bits go to 0 because we have moderate decay in x. I'm just reminding you the global picture. So this is bounded by e to the minus 2 pi xi minus m. Let's see, xi minus m y. And that's true for any y. For any y. So send y to infinity. This is a positive number. That makes this negative. So this goes to 0. So if xi is bigger than m, we get that the Fourier transform doesn't exist there. I mean, is dead there. Right? I'm just reminding you quickly of the argument. That was if we had these extra assumptions. If we only have not this assumption, but the assumption that f of x plus iy grows at worst like e to the 2 pi my, then what we use is this. We give ourselves, we don't have this decay, so we can't justify pulling contours because the bits on the end, when we send those bits out to infinity, we don't have control on how they go. They're just bounded, but they're not integrable. So things aren't going to 0. We can't pull contours, but we modify the argument by giving ourselves the thing that we're missing with an epsilon. So this has f hat supported, f hat of xi is 0 for xi bigger than m. And this converges to f hat of xi as epsilon goes to 0. Okay? So first assume we had much better decay. Great, it works. Then, well, you don't have it, so you give yourself the better decay, and then the argument works. And finally, the last step was that this actually implies, the last step was Fragment-Lindelof. Fragment-Lindelof says, let's do it in a sector like this. We proved it in a slightly different sector just because that's the easiest place to set it up. But in a sector like this, if, let's say, big F on the real line, on the positive reals, is bounded by 1, and big F on the imaginary, positive imaginary line is also bounded by 1, I would like to conclude that F is everywhere bounded by 1 in the interior. Let's call this S. This is on all of S, but it's simply not true. It's simply not true unless I make one extra assumption.
On the growth of F?
Exactly. It can't grow like e to the z squared. E to the z squared is the prototypical function that has both of these conditions and yet blows up on other directions. So I need to know that I grow slower than e to the z squared. Let's say some other constant. Well, we could say z, but actually z to the 9/10 would also be, z to the 19/10 would also be okay. We don't need it. We're only going to use that it grows at most like z. And so we proved this, and hopefully you remember how we proved it. We multiplied by a slightly larger power. We multiplied by a slightly larger power that was still less than 2 and controlled the angle. And that told us that when we multiply by this thing, you get something that decays. And so it has a maximum. So it has a maximum on the boundary, but on the boundary, it's bounded. That's like a crash version of crash course on Fragment-Lindelof. Okay, I'm just trying to remind you how this worked. So if this is true, now look at our original function. So back to our little f, back to little f of z. This is what we went over very quickly last time. It's bounded by some constant e to the 2 pi m z, but let's rescale so that this constant is 1, just to make things simple. So imagine that c is equal to 1 after rescaling. So I know this bound, and now I'm going to let capital F of z, be little f of z times e to the 2 pi I m z. Okay, this is a nice holomorphic function in this region S. Okay, it's a nice holomorphic function in this region S. What do I know about it on the positive reals? Can I bound this by something? Yeah, and f also has moderate decay. Remember, we said f has moderate decay. So f of x on the real line decays like 1 over 1 plus x squared. In particular, it's at most 1. Ishan, I'm missing something, or it's okay? Something you don't like?
No, I missed part of, I only watched the first like 20 minutes of the previous lecture, so
Okay, I understand.
I'm zoned out. Yeah,
All right.
I'm waiting for conformal mappings.
Okay, all right, I'll get there. I'll get there very soon, I promise.
Okay.
Okay, so on the positive reals, this has absolute value 1 because it's e to the 2 pi I times something real. This thing is bounded by 1, so the whole thing's bounded by 1. On IR plus f of IY is bounded by, well, this thing is always bounded by e to the 2 pi m z, but z is y. And this thing is exactly equal to e to the minus 2 pi my. And so this is equal to 1. So this is a function. This is a function. It grows at most exponentially. It's bounded by 1 here. It's bounded by 1 here. That means it's bounded by 1 everywhere. That means f of z is at most 1 for all values of z, but this in absolute value is equal to the absolute value of f of z times the absolute value of this is the real part, and the real part is e to the minus 2 pi m y. And so I move this to the other side, and what we've shown is if we only assumed exponential decay in z, or at worst exponential growth in z, then that implies at worst exponential growth only in the imaginary part. Okay, that's for moving this to the other side. So that's the Fragment-Lindelof. Fragment-Lindelof lets us get from e to the 2 pi mz growth to at worst e to the 2 pi my growth. Then we're in position to apply the second argument, which uses the first argument to get us the full Paley-Weiner theorem. Okay, any questions on Paley-Weiner? Make sense? All right. Very important theorem. And introduces a lot of, almost more important than the theorem itself, although the statement's very important, is the techniques. Some of these techniques are really instrumental. Yeah, let me just make one quick remark. Let me make a quick remark. I'm not going to prove this, but you can look through the proof in the book if you like. Let me not make this remark. Let's move on. We want to get to conformal maps, right? That's what you people paid good money to see some conformal maps. So let's get to it. Let's move past this Fourier analysis stuff. Conformal mapping theorem maps. Okay, definition. So F from, we have some subsets U, V. U and V for now will all be subsets of the complex plane. F is called conformal if it's holomorphic. Well, really, I mean, there's a funny thing. We're going to use slightly non-standard terminology. Conformal means the angles are the same. And what we proved almost on day one is that holomorphic maps are automatically angle preserving, with one slight exception, which is that, well, I'll make the statement in just a second. So a function from two sets is conformal if it's holomorphic and one-to-one, let's say. Let's go straight to bijective. Let's just define it to be and bijective. Okay, so it's one-to-one and onto. So I have a bijection between these two sets, and that bijection is a holomorphic function. Okay, some people say just that it's one-to-one, which means if we restrict V to the image of F, the range of F, then it'll be onto, obviously, by definition. And by the way, the range is open because
holomorphic functions are open maps.
Open mapping theorem, exactly. Holomorphic functions satisfy the open mapping property. Okay. So let's just go straight to defining it as bijective. We will not ever care about if V was bigger than you had in mind for it to be, just forget it. All right. So the only difference between holomorphic and conformal is now we're adding the adjective bijective. They're automatically conformal, right? Conformal, angle preserving. We discussed on day one that these things are angle preserving. Okay, and definition.
Professor?
Yes.
Wouldn't z squared for the punctured disk be conformal, but not one-to-one?
So it would not be one-to-one, and hence it would not be conformal. And actually, it's not angle preserving at exactly one place.
I'm removing the 0. And then,
So, but it's not one-to-one. It's not one-to-one on the disk. It is one-to-one on a half plane. So the function z squared is perfectly fine as long as you stay away from the place where the derivative vanishes. That's going to be the next lemma.
so the punctured disk or the Like,
Yeah,
what
so
if we
you want U to be the punctured disk, and you want F to be the map Z goes to Z squared.
Yeah.
And where does it land?
Onto the punctured disk?
Okay. And is it 1-to-1?
It isn't, but it is angle preserving, it seems.
Right. So I'm defining conformal to be 1-to-1. I want more than just angle preserving.
Okay, I see.
Right. So it's
Why do we
conformal.
want 1-to-1?
Sorry?
Why do we want it to be injective exactly?
Because we want a definition that two sets, U and V, subsets of the complex plane. We want to do, we're sort of moving away from analysis into geometry, or rather topology, as you'll see. U and V are conformal. Two sets are conformal if there exists an F that's conformal between them. So if it's bijective, then it obviously has an inverse. I mean, this allows us to make an equivalence relation, right? Which, so the question is, which, so is U conformal to V, conformal, an equivalence relation? Of course, right? You have two things. There's an F from U to V. There's an inverse.
Why is the inverse holomorphic?
Yes, bingo. There's something to prove. There's something to prove. Is F inverse holomorphic? We know there's an inverse. It's a bijection. Bijections, by definition, have inverses. You're 1-to-1, you're onto, so that every point has an inverse. Okay, we have a well-defined inverse function. Is it holomorphic? So now we need a couple of lemmas. Lemma. Assume F from U to V is holomorphic and 1-to-1. Then the derivative of F is never 0.
Professor,
Please.
is it the case that an angle preserving map is necessarily holomorphic?
It is not the case that an angle preserving map is necessarily holomorphic, because the classification, let's think for a second. Angle preserving, I mean, okay, this is the thing about, if it does satisfying the Cauchy-Riemann equations, is that enough to deduce holomorphicity? So you need slightly more than just that you satisfy the Cauchy-Riemann equations. So conformality is almost equivalent to the Cauchy-Riemann equations, because if you look at what the linear map is, right? You have some linear map. Should we have this aside? Okay, so pause this lemma for a second. Aside. Remember how this whole business got started. If you have a function f of z, then locally, in a neighborhood of z0, f of z is f of z0 plus some linear map of z minus z0 plus lower order. Right? That's what it means to be differentiable in the R2 sense, approximable by a tangent plane. So this is R2 differentiable. And this is a linear map. It's the partial derivatives. So it's the derivative of u with respect to x, derivative of u with respect to y, derivative of v with respect to x, derivative of v with respect to y, right? This is this matrix. F is u plus v, u plus iv, and z is x plus iy. Whoops. Right? So this is this matrix of partial derivatives. What does it mean for this to be conformal? Remember, we had this classification. This can be written as a unipotent, something that's unipotent, something that's diagonal, and something that's a rotation, like cosine theta, sine theta, minus sine theta, cosine theta. and maybe a sign, plus or minus 1, right? And conformal means there's no shearing. That takes rectangles to parallelograms, so that ruins angles. These things have to be the same, or else it takes squares to rectangles. So it changes not in any one of the directions, but it changes the diagonal angle. So these two have to be the same. And this is rotation. So it's rotations and dilations, basically, locally. Rotations and equal dilations. Well, that's equivalent to, I mean, right here, this rotation, the dilation is some uniform thing, but this shape is exactly the Cauchy-Riemann equations. These two, the diagonals are equal and the off diagonals are negative. Okay, so asking things to be conformal is the same as asking for the Cauchy-Riemann equations to be satisfied. So if the Cauchy-Riemann equations are satisfied and your function is R2 differentiable, then it's holomorphic. So conformal is almost equivalent to holomorphic, modulo this nonsense about you might be holomorphic at a point but not in the neighborhood of a point, and then you might be conformal at a point but not in the neighborhood of the point, and then you're not holomorphic.
Okay, so then for bijective holomorphic map, we know it's inverse map. I mean, preserving angles is, if it preserves angles going one way, of course it preserves angles going the other way.
This isn't going to be a hard proof. Yeah.
Is it just that we need to know that it preserves angles continuously in some sense?
In a neighborhood. Yeah, basically. Yeah. This is not going to be a hard proof. Okay. So here's the lemma. So let's prove this. In fact, we'll prove the contrapositive. So assume f hat of z0 is 0. Okay, assume there exists a z0 in U so that f hat of 0 is z0. So again, here's our picture. Here's U. Here's some shape U. F maps it to whatever V is. And the question is, are they holomorphic? So here's a point z0 and the derivative at z0. So let's call this, I don't know, w0, f of z0. And the derivative here vanishes. Okay. I want to prove from that the function can't be one-to-one in a neighborhood of this point. That's exactly what's happening to z squared. If you remember to Ishan's question, it's exactly what's happening to z squared. At 0, z squared that's the only place where locally z squared is taking angles and wrapping them around themselves. Okay, everywhere else, locally, it's one-to-one. Globally, it's not, because there's a place where it allows it to wrap onto itself. All right, so we're going to see this. So locally, near z0, we have that f of z is equal to, it has a power series expansion, f of z0 plus f prime of z0 times z minus z0, and so on. Of course, this is 0. That's the assumption we just made. So this is equal to, let's call it f of z0. Now, I don't know what the next order term is. So there's some ak z minus z0 to the k, where k is at least 2. This coefficient is non-zero. And then a holomorphic function g of z, which is big O of z minus z0 to the k plus 1. Okay, the rest of the Taylor series. Does that make sense? And so now I want to look at the function. I want to know, am I one-to-one in a neighborhood of W0? So let's take W. Let's take W to be very close to W0. Let's take W. I want to call this W plus W0. I want to call this point W plus W. It doesn't matter. It doesn't really matter. Let's call it W. Let's call it W. So for W near W0, let's look at the equation f of z minus w. One more thing I want to say, I can look at this neighborhood. So near z0, there's a neighborhood. The function is not constant. I mean, it's not, the constant function is obviously not 1-to-1. So f is not constant. F is not constant. The constant function is not 1-to-1. So near z0, in a neighborhood of z0, there's one point where it vanishes, but there's no other. Near z0, f prime of z equals 0 implies z equals z0. Okay? In other words, the derivative never vanishes except at z0. If we had a limit point of where the derivative vanishes, then the derivative would everywhere be 0 and the function would be constant. Okay. So let's look at this. I want to know, do I hit this point W? Well, or what's the multiplicity of this point W? So, so let's think about this as W. I'm going to write W as W0 plus eta. I don't know. W0 plus eta, where eta is small. So this f of z minus w is f of z minus w0, which is z, f of z0. This is w0, f of z0 minus eta, where eta is some small complex number. Okay, this difference is eta. Does that make sense? Okay, now f of z minus f of z0, from here, f of z minus f of z0, that's equal to a k z minus z0 to the k. I'm subtracting off eta plus g of z. So far, so good. Now I want to call this function capital F of z. Now, as z goes to z0, this thing, so on the boundary of a disk of some small radius epsilon around z0, what do I know about f of z? I claim that f of z on this boundary, so I need my picture again. I'm going to zoom in on this picture. Here's W0. There's some disk of radius epsilon about W0. About W0. Sorry. On a disk of radius epsilon about Z0. So the function's continuous. So as I get closer and closer to here, I get closer and closer to here. On this boundary, big F of Z, this is going to eta. Eta is small, and G of Z is going to 0. So I claim that this will be always bigger than G on the boundary. This is going to 0 as Z goes to Z0 in a neighborhood of Z0. And this is going to eta. And eta is some small non-zero thing. Okay? So what do I know about functions where f dominates g on the boundary of a disk?
The sum of their functions have the same number of zeros as the original.
Bingo, beautiful. Remember whose theorem that is?
Someone from a long time ago.
Someone from a long time ago. Someone from.
Is that Roche?
Ruchet. Okay, yes. So Ruchet. Ruchet's theorem says that f and f plus g have the same number of zeros. In the disk. Okay, how many zeros does F have in the disk? K is bigger than 2. We can solve for Z, right? We can solve this for Z. F of Z equals 0. I mean, I don't have to do it out for you, right? Eta over A and then raised to the 1 over K power and then add on a Z0. So this has K, which is at least 2 roots. And that implies, so this F plus G has at least 2 roots, which means F of Z minus W has at least 2 roots. F of Z minus W has at least 2 roots. This was the same issue. I mean, we basically talked about this when we proved Rochet's theorem. We talked about what happens if there are multiple zeros. The function is one-to-one if the zeros are simple. But if the zeros are not simple, which happens exactly when the derivative vanishes, if the value if it takes multiple values, then you get more roots. So F of Z minus W has at least 2 roots in Z, right?
Professor?
Yes.
Do we know that these roots are distinct?
We do not yet know that the roots are distinct. Are they distinct? Are they distinct? So if not, then we have multiplicity. Then F of Z minus W has multiple roots. If not, then F of Z minus W has multiple roots.
I see where this is going.
Which means, go ahead.
It means that it's going to raise K. The power series for F will have, you'll be able to factor more factors of Z minus Z naught out of the power series.
Well, this is no longer at Z naught. It's at wherever. I mean, I don't know what the pre-image of W is. At some point, let's say has at least 2 roots. Let's say one of them. Let's say one is Z1 and the other is Z2. Has at least 2 roots. Let's say that the 2 roots are Z1 and Z2. Are they distinct? If Z1 equals Z2, if not Z1 equals Z2, then I claim that we know something about the derivative of F at Z1.
It's 0.
It's 0. But we said F doesn't vanish in a neighborhood of Z0. Okay? But F doesn't vanish. F prime in a neighborhood of Z0 doesn't vanish. Okay, so that's the contradiction, if you like. I mean, it's not really a proof by contradiction. It's more of a proof by contraposition. But if you're one-to-one, you're one-to-one basically if and only if the derivative doesn't vanish. Okay.
Sorry, real quick. Why is it 0 at Z1? Something to do with the power series?
Yes. So it has a double root at Z1. The function. So let's unpack this. Locally, it has a double root. This function has a double root as Z goes to Z1. F of Z minus W has a double root, so is big O of Z minus Z1 squared, right? If not, then this thing is then F of Z minus W is this as Z goes to Z1. Does that make sense, Thomas? And what does that mean? But this has an expansion near W. It's equal to, so F of Z near Z1, F of Z is equal to F of Z1, namely W, plus F prime of Z1 times Z minus Z1 plus lower order. And so this difference, if this difference goes to 0 as a quadratic, then this thing, which only goes to 0 as linear, must have this term be 0. Does that make sense?
I think so, yeah.
Great. Okay, so we used Richet to produce at least a second order vanishing. That vanishing cannot be at the same point because otherwise that derivative would vanish. And we said we zoomed in on a neighborhood where the derivative doesn't vanish. That means these two roots are distinct, and that means the function is not one-to-one. So if you're one-to-one, then the derivative doesn't vanish. If you're one-to-one, then the derivative doesn't vanish. Okay, let's quickly prove, and then we'll take a break. Let's quickly prove that that this is indeed a equivalence relation by showing then a corollary that the derivative is holomorphic, that the inverse is holomorphic. So lemma, if f is conformal, so holomorphic and bijective, then f inverse is indeed holomorphic. Okay. Proof. Okay, let's write G for f inverse, and let's look at G of W minus G of W0 over W minus W0, right? So the limit of this is G prime of W0. So far, so good? Okay, I'll write this as 1 over W minus W0 over G of W minus G of W0. W is the image of f. W is, so if I have W0 is f of Z0, I'm just keeping the same notation as before. Let W be a point that's in the image under Z0 of f, and W0, and W be the point that's under the image of Z under f. So then I'm just putting these back in as they were. Over G of W will get me back to Z0, Z minus Z0. Does everybody see that? And what does this converge to? As Z goes to Z0, in other words, as W goes to W0, that converges to 1 over f prime. Hello. 1 over f prime of Z0, which is only okay as long as
F prime is not 0.
f prime doesn't vanish. Perfect. Okay, and we know from the previous lemma that f prime doesn't vanish. So it's the non-vanishing of this derivative that tells you that the inverse function is differentiable. This is like, I mean, you could sort of think about this as high school. If you have this, then you differentiate both sides. So you have the derivative of f of g of z, chain rule times g prime of z equals 1. In other words, so g prime of z is 1 over f prime of g of z. Well, I'm using w's instead of g, right? This is the limit of this is g prime of w. So this goes to g prime at w. And it's 1 over f of w0. F of z0, which is also 1 over f of g of f prime of g of w. Let me write this one last time using the same variables as up there. 1 over f prime of g of w. And I guess I did this at 0, at w0. Okay? So this is a familiar formula. All I'm trying to say is this is something that's not new. We're just doing it from this other perspective. Any questions?
Professor,
Please.
there are many ways in complex analysis to show or holomorphicity, right? Is there some really fancy way to show that F inverse is holomorphic, which works using complex analysis?
I mean, in a sense, we have the chain rule in complex analysis. And so this equation already tells you what the derivative must be. And the derivative is 1 over f prime at g. And 1 over f prime never vanished by the previous lemma. So if f prime vanished, then 1 over f prime would indeed be blowing up. And so the derivative would not have a limit.
I was
I mean-
thinking more, say, some kind of fancy contour integration where it just pops out that like.
You want to do something fancy when something as simple as the definition already gets us there?
Like, sure, but like the definition like doesn't. I don't know. I feel like I don't see why it has to be 1 over the derivative. Like I kind of do, but like it seems that there may be another way to see it.
All right, let's take a break and talk about it. So let me pause. All right. So let's see some examples of conformal maps, and maybe we'll see some computer versions of those later. But okay, so examples. Here's kind of the prototypical conformal map. This is the upper half plane. Upper half plane, z equals x plus iy, and y is positive. Here's another region, the disk, set of z with z being at most 1 in absolute value. Now this is non-compact, this is non-compact, whereas this is compact. So there's no way there's a conformal map between the two. Take the function that takes z in the upper half plane to z minus I over z plus I.
The open disk is not compact.
It's not compact, that's true, but it's bounded. Yeah, you're right. The closure is non-compact. Let's see, non-bounded, shall we say. I'm trying to, push your intuition about these things. Yeah, it has nothing to do with boundedness. Conformal, you can have conformal maps from all kinds of strange regions to others. All right, let's look at this. I claim that this y, so is this in the disk? I claim this is a map from the upper half plane to the disk. So we have to show is the absolute value of z minus I over z plus I less than 1 for z in the upper half plane. Is this true? Is there an easy geometric reason for this to be true?
The distance from I is
Perfect.
less than the distance from minus I.
Perfect. The definition of the upper half plane is that you're closer to I than you are to minus I. Z minus I is smaller than Z plus I. See that? Okay. So so distance to 2I is less than distance to minus I if and only if you're in the upper half plane. And that, of course, is what tells you this. Okay. Is this map differentiable? Is F holomorphic? Yes, it's a nice, this is, anybody know what this kind of map is called? Have we talked about these yet?
Mobius transforms, I think.
It's a Mobius transform. Yes, this particular shape.
Fractional linear.
Fractional linear, exactly. It's a fraction of linear maps. Fractional linear. It's a linear map on top, a linear map on bottom, and a fraction. So is it holomorphic? Well, where does the denominator vanish? Negative I. Negative I is not, so if this has a pole at negative I is not in the domain. And so yes, holomorphic. Is it bijective? How about the derivative? Does the derivative vanish? Or is there an inverse function that's holomorphic? There's a variety of ways of trying to do this. So what's the inverse function? If W is equal to Z minus I over Z plus I, then Z equals what? Okay, want to take 10 seconds and do the algebra? And then I'll show you how you could have done the algebra in 2 seconds instead of 10. Give me a thumbs up when you have the formula. Okay, I got 2. Got 3. Anna, you want to tell us what you got? Oh, I can't hear you, but it doesn't say that you're muted. I don't know if your mic isn't working. You gonna put it in the chat? Yep, there it is. Okay, so perfect. Let me so that's perfect. Let me try to derive it in a slightly different way so that we see some other. There's many ways of writing this inverse function. Let's just do it all together. It takes 10 seconds. WZ plus IW is Z minus I. I'm just multiplying this over there. WZ plus IW equals Z minus I. I'll move the Z's to this side, the I's to that side. Maybe the other way around. I'll move this. So I'm getting an IW plus I. I don't want parentheses. I want to separate things. So I get an IW plus I on top, and I get a Z minus W plus 1 on the bottom. W minus 1 on the bottom. So I moved, let's see, I moved this over here. I'm going to move that over there. That becomes a minus W plus 1, which is the same as what Anna wrote. Now, here's how you could have done this in 1 second. The nice thing about fractional linear maps is that you can express them in terms of matrices. So let's give an action. I'll give an action of, well, 2 by 2 matrices, let's say with complex entries, acting on the complex numbers, which is if I have a 2 by 2 matrix, A, B, C, D, acting on some point Z, by definition, this is the general fractional linear map. It's AZ plus B over CZ plus D. Now, what I mean by an action, let's leave this as an exercise. It's a fun one. I'll basically end up doing it for you, is that if you have two matrices, G1, G2, and you multiply them, and then you act on Z, it's the same thing as taking G2 acting on Z. That gives me now an element of C, and then I can act on that by G1. So if I have two matrices, actions are the same as multiplying. That's what it means to be an action, is that the group action agrees with the action on the space. Okay, and what that means, now what about the identity matrix? What does the identity matrix do? This is 1 times Z plus 0 divided by 0 times Z plus 1. That's very good. The identity matrix acts as an identity. And so let's see the consequences of this. If we want to know what the inverse is, all we have to know is the inverse matrix, right? The inverse matrix will have, therefore, G inverse G acting on Z will be Z, and therefore G inverse acting on G of Z. This is the inverse map of F, of G, whatever G is as a matrix. So what is the matrix of this? So if F of Z is a fractional linear map, Z minus I over Z plus I can write that as a matrix acting on Z, where what's the matrix? Ishan, you're muted.
1 negative I, 1 plus
Yeah,
I.
you just read it off. Exactly. You just read it off. There's a 1 in front of the Z, and then a negative I, and then a 1 in front of that Z, and then an I. And so what's the inverse matrix? So F inverse of Z. I just invert a 2 by 2 matrix. You know how to invert matrices, right? The inverse of A, B, C, D, you switch the diagonals. So I goes there and minus, and 1 goes there. These two switch. These two get negated. These two get negated. I negative 1.
Divide by determinant.
And you must divide by the determinant. But here's a magical thing that happens. If I multiply all of these by a constant, that constant is gone. So I don't have to divide by the determinant. And look at the map that we wrote down. This inverse map is exactly I, negative 1, 1. Okay, so that's how you could have done this in 2 seconds instead of doing any algebra. You just see that this is this matrix, 1 negative I, 1 I, 1 negative I, 1 I. You flip these two, the I and the 1 flip, the negative I negates to a plus I, the 1 negates to a minus 1. Okay, does everybody see that? So, okay. So there's something funny that's happening here. Why does this work? Why does this work? So really, it's not, we don't really want to think about these matrices. We want to think about, for this map to be invertible, I need not the matrix, not any 2 by 2 matrix. I need an invertible matrix. So I need a general linear GL2C for there to be an inverse. We want holomorphic conformal maps that are invertible. And what we just said is it doesn't matter if you multiply through by a constant, it doesn't matter. That's the group PGL2C. So PGL2C is you take all the matrices in GL2C, all 2 by 2 invertible matrices, determinant is not 0, and you mod out by multiplication by non-zero complex diagonal matrices. That's the center. This is the center. Z is the center of your Lie group. And why? So let's do this exercise the right way. There's the wrong way, which is literally to put in A, B, C, D and alpha, beta, gamma, delta and multiply it out and verify that you get the same thing. The right way to see this is really what's going on is that there's an action of GL2C on not C, but C2 pairs of complex numbers, which is the obvious action, just ABCD acting on ZW is matrix multiplication, AZ plus BW, CZ plus DW. Except what we want is a projective action. So this descends to an action of PGL2C on the projective complex line. So what do I mean by this? By this I mean pairs, so you take C2, you can't have the 0, 0 vector, so there's no 0, 0. You take away 0, 0. And two things are the same if they differ by a complex number. In other words, ZW in P1C, I should really put brackets here, is equivalent to lambda Z, lambda W for any non-zero complex number lambda. That's the equivalence relation. Okay? And so does PGL2 really act on, so let's understand this complex line. So this is the projective complex line. What does it really mean? So if I have ZW, and let's say W is not 0, what could I take for lambda? This will be the same. The equivalence relation says this is the same as something.
W inverse.
I could take lambda to be W inverse, which means I get a 1 and then a ZW inverse. And this is just an arbitrary element of C. So one chart of the projective line is just C itself. And there's another chart. You have two options here. Or if W is 0, that means Z, we don't allow 0, 0. Z is non-zero. And that's similar to, that's equivalent to, I could take lambda now to be
Z inverse.
Z inverse. So I get 1, 0. And this is the point at infinity. So this projective line is exactly the same thing as C adjoin a point at infinity, or which is exactly the same as the Riemann sphere. Okay, this North Pole is exactly this extra point that we add to the complex plane to turn it into the complex projective line. Okay, and now let's look at the action. So if I have this action, let's say W is not 0, then this point AZ plus BW, but I can make W equal 1, then that's equivalent to W equals 1, and then CZ plus DW. But that point in projective space is similar to, let's say this denominator is not 0. I can put a 1 and AZ plus B over CZ plus D. If it is 0, then I just get the point at infinity. And if it's not, then I get the fractional linear transformation. So that's exactly why the fractional linear transformation is an action. It's an action because matrix multiplication is an action. I can multiply matrices like this, and I multiply by another matrix, and matrix multiplication is associative. You can put parentheses here or here, and you get the same thing. Does that make sense? So this is the beauty of fractional linear maps. They're just maps on the complex projective line under the projective general linear group. Does that make sense? And it's exactly what's going on with this Riemann sphere complex plane stereographic projection picture. Okay. Let's look at one more thing in this map. So we have this nice map, F, which takes Z to Z minus I over Z plus I. So here's the upper half plane. We just argued that it takes it to the disk. Because it has an inverse, F inverse takes W in the disk to, what was it? We can read it off here, right? You flip the off diagonals, I1, so IZ, and you negate the, you flip the diagonals, you negate the off diagonals. Plus I negative W plus 1. Okay? And if W, so let me leave it as an exercise that if W has absolute value less than 1, then this thing has imaginary part, which is bigger than 0. That's a fun little exercise. What I want to understand is what happens to the boundary. So one way, a good way of understanding conformal maps, good way, pre things like Mathematica, before computation, where you could just have the computer draw this for you, a good way to analyze these, is what happens on the boundary. Look at the boundaries. Okay, so what happens to the point 0? Where does 0 go under this map? Zero minus I over 0 plus I.
One.
Negative I over I. Yeah, now people are holding up the right symbols. Here, let's put some. Yeah, so this is negative 1. So this is f of 0. Right? This is 0, this is f of 0. How about the point 1? One minus I over 1 plus I. Anybody want to tell me where that goes? Should we compute it together?
I
What is it, Kailash?
post to minus I.
Minus I, perfect. That's f of 1. How about negative 1? Where do you think?
1.
Ooh, negative 1, you want to send to 1? So I have negative 1 minus I over negative 1 plus I.
I meant I.
Oh, I, sorry. Yeah, so this is f of negative 1. And of course, everything in between, there's this in-between region that's going to go to the in-between boundary. And the same thing here. This in-between region is going to go to this in-between boundary. What about infinity? What about infinity? All the way over here somewhere. Infinity minus I over infinity plus I. Infinity over infinity. Yep, you guys see that? Hello. This is f of infinity. Okay, and there's this whole region, which is this whole region. Infinity is a perfectly fine point. Infinity is just 1, 0 instead of z1. So it's a point like any other. That's the beauty of projective space. Okay, so we've sort of analyzed this boundary. You can see this analytically. Let's just do this analytically. Let's see. If x is real, so what is f on the real line? This is, so this takes x to x minus I over x plus I, which we can simplify, multiply top and bottom by x minus I. On top, I get x squared minus 1 plus, I guess, minus 2xi. And in the bottom, I get x squared plus 1. And so this is the real part. This is the imaginary part.
Professor,
Yes.
Would it be easier to notice that the top is the complex conjugate of the bottom, and hence the division has to be magnitude 1?
Yep, that'll tell you that it's symmetric from the top to the bottom. What goes to 0? How about this point 0? Yeah, because it's right here. How does this thing give a 0? It gives a 0 when z is I. So this point I maps to 0. Okay, so the interior is mapping to the interior. You can sort of analyze the boundary. Here, the next calculation would be that the sum of the squares of this and this is 1. This is just algebra. Algebra, x squared minus 1 over x squared plus 1 squared plus negative 2x over x squared plus 1 squared is equal to 1, which is blatantly obvious if you look at the numerators and compare it to the denominators. Okay, so that what that means is we're getting points on the boundary. It maps this boundary. This is the boundary of H. I mean, plus the point at infinity maps to this is on the boundary of the disk. All right. Let's do we have time for, we can do one more, maybe. Well, you asked about x squared. So let's look at z squared. Let's look at one last example. F of z equals z squared. So here we have to be careful. If we write z as r e to the I theta, z squared is r squared e to the 2I theta. So let's say theta is between 0 and pi, so that 2 theta is between 0 and 2 pi. So this will be a conformal map from, if theta is between 0 and pi, 0 is here, pi is here. This will be a conformal map from the upper half plane, but not a neighborhood, not some removed neighborhood of the disk, to the entire complex plane, but missing theta equals 0. So the slit plane. The slit plane. Okay, what happens to 0? What happens to 0? 0 squared is 0. Any positive number squared. Any positive number squared. Positive number squared remains positive and squared. Any negative number squared remains negative and squared, but they're on opposite sides of where that cutoff happens. Because we don't really have negative numbers. We have negative numbers are the limits of things with theta very close to pi. So their squares will be things with very close to 2 pi. That's why I'm drawing them above and below. You see, so that straight line gets folded. I can't do it with my hands. That straight line of that gets folded like this into the, that's the largest region on which this map is 1-to-1. Does that make sense, Ishan? So that's why you can't take the disk in the neighborhood. Okay, and for example, I meant to give a new color, but whatever. I squared will be -1, so this is f of I. Okay, this is I squared going to -1. That's this conformal map. All right, we are going to see a whole bunch more examples of this, and then we're going to try to determine when two shapes, when two open domains are conformal to one another. And that is the subject of the Riemann mapping theorem. Any questions?
Earlier I thought that the fractional linear transform was a Mobius transform. I had the impression that Mobius transforms were fractional linear transforms. So what's wrong with that? What are Mobius transforms actually?
So there's a notion of an extended Mobius transform, which allows orientation reversing. All fractional linear transforms are orientation preserving. And Mobius transforms, sometimes people think of just circle inversions. And these things in general are combinations of pairs of circle inversions, basically. So you have translation, you have dilation, and you have rotation. These are the kind of primordial conformal maps that make up Mobius transformation.
I see. Thanks.
Other questions? All right. I